We're going to see now the concept of the transfer function, and we're going to start with a little circuit that we were doing a bit earlier. As you notice, what you have on the screen is the derivation of the differential equation, and in the previous video, in the previous lecture, we had actually converted this differential equation into a block diagram. Now we're going to use the same example to look at the transfer function. And since I like these steps, let's begin writing steps to do that so that we do things right. So in here we close this, so we concentrate on this better. First step is consider the Laplace transform. Let's say Laplace transform. Okay, what I would like to do is perhaps use my ability to draw a line in here nicely and divide my notes here on the left hand side, on the right hand side, so I can actually separate what we're doing here. Let's just keep it like that. And concept of the Laplace transform. What does it say? Professor Laplace was a professor at the University of La Sorbonne in Paris. He came with the idea that we could have a representation of differential equations in an algebraic form. And to achieve that, he came up with either what we know as the Laplace operator, or with the Laplace transform that says that the variable s implies the derivative of any function. So if you have a function that has a derivative is d dt. If you write it like this, s squared means the derivative of a derivative, see? Like that. So if you have something like a function of time that we have in the time domain, that the dq dt in fact could be represented as s times the variable q in the s domain. See? And then if you have d squared q dt squared, this would be the s squared, because it's times q of s, like that. Just always keeping in mind that you have this variable as the basic one, that s is the q dt. So if you have it in here this way, we could transform the differential equation in the Laplace domain. So Laplace transform is here. We're going to make just a little note. Express the, maybe let's put it in number 2 to make it a little more organized. Number 2 is express the derivatives in the S domain. S domain or Laplace transform is the same thing. So if you do this, then what are we gonna what can we write in here? Uh, for example, an objective. Let's say in this case, define the objective. Define the objective, and define the objective is the relation between a variable output to the system input. Okay, so this relationship between a variable output is called a transfer function. Okay, so for this purpose of this example, we're going to say find the relation between the voltage on the capacitor, voltage C, and the input B. Very good. So in order to do this, you first realize that the voltage on the capacitor, we see that this is 1 over C times the integral of I dt. Yeah. So it follows that if this is the derivative, the integral of a function, some function, the I dt, is the opposite of the derivative. So this is 1 over S. So if we express this in the Laplace domain, to be able to find the relationship between B sub C and V, we need to express both of those in the Laplace domain. Okay, so let's start with the first one. The first one in here, if you the first one in here you have is maybe let's change some color to make it more appealing to, a little easier to read. B of C in the S domain is 1 over C times 1 over S times Q of S. Yeah, that's that one. The other one, the voltage, the V, this voltage V is equal to what do we have? R times S times Q of S plus we have 1 over C times Q of S. See, I'm looking at the one on the left hand side. I'm looking at this on the over here. See, I'm looking at this. So we have in here plus, what do we say, L times S squared times Q of S. See? So now what you can do is you can write the equation here a little more in, we have both of those in the S domain. And now we need to find the relationship between those two. So I would, in the steps that we're doing, I would just add the last one, find the relation between No, I already wrote it. Find the between B, C, and B. We need to find this relation. Okay. So what? How can we do this? So you write in here that B of S is equal to R times S plus 1 over C plus L times S squared, and this is Q of S. Yeah? The relationship between those two you will say that B of S, BC of S is equal to, relationship to B of S like this. Is equal to, what would you say? This is 1 over C times 1 over S divided by what? LS squared plus S times R plus 1 over C, right? Or you could go farther. You could go and do this. This is 1 over, what's this going to be? This value. L is squared plus R times S plus 1 over C, and then multiplied by what? S times C, right? So you could write this like this. That this would be just to write it in a polynomial form, this could be S cubic, so L times C times S cubic, plus the other one would be C times R times S, right? RC times S squared plus, what do we have? Plus S, right? So this would be the transfer function that we want, this relationship between voltage of the capacitor, this relationship like this. Sometimes it's expressed in the way it is just in here. You could leave it 1 over CS and then over LS squared plus S times R plus 1 over C. And this would be this ratio right here. This is your transfer function. And then you may say, what are you going to do with this? Huh? What are you going to do with this? In this case, you could see that the voltage C of S is equal to the transfer function times the input, right? See? So this is saying basically to you that an output on the system is equal to the transfer function times the input. And that's the contribution of Laplace, major contribution. Because if this is true, remember the simulation of the voltage across the capacitor that we could do in the Simulink. In here, if we use the transfer function, we should be able to get the output also. By giving it a step input, we should be able to do that. So what I would like to do is, I'm going to go back to MATLAB in here, to the MATLAB prompt, and you're going to learn some commands in here to be able to put this transfer function, just like we put the block diagram into MATLAB. I'm going to do the same thing, but with the transfer function now. I want to make it small in here so that I guide myself on how to describe it here. See right there. Okay, so here's what I would do. You see here, this has a numerator and it has a denominator, right? And we could write this in terms of the polynomial as it is. We could just write it in, like I said, in terms of the polynomial that it is in there, and do the calculations using that. Okay, so what I would say is let's hold on for a second. I think we have I just discovered we have a small error in here. Let's review something in here, because I want to make sure that I don't misguide you here. And if you need to correct something, then we need to do that. So this is 1 over c is 1 over s, the integral. See, the problem is that I is dq dt. So here's my small mistake. In here, this 1 over s should not be here, because you see the equation is like this. See, I wrote it correctly here, but not over here. This is the when you integrate I, you get q. So in reality, this is just 1 over c times q of s. I think we need to make that correction, because otherwise we'll have the simulation would be messed up. So why don't we do that real quick, and then we'll do this. So see here, there's the raise. It's just erased. That's all I'm saying. This is all we need to fix. But that, of course, is going to affect the one down here, right? See this one right here. So what we don't have is this s. This is, yeah. It's 1 over c, and then that's all the correction I needed to do. So here's what I would do. I'm going to define the numerator of this transfer function as 1 over c, which was 1 over 1, right? C was 1. And then the denominator of this transfer function is going to be what is L? 1, right? And then what was R? 0.5. And then 1 over C is of course 1. And then we'll do this real quick. So now we are going to define the transfer function G. It's called transfer function of the numerator and the denominator. And what this does, see, it gets this transfer function like that. And if I do this, if I do the step of the transfer function G, I would get the response based on this transfer function. And the computer is going to plot this for us in just a moment. We right there. So with this we finish this explanation.